We present long-term human motion prediction with scene context. Human movement is goal-directed and constrained by the spatial layout of the objects in the scene. Our motion is also multimodal. In the same situation, we can take different future actions to achieve different goals. In this work, we seek to understand such goal-directed, spatially contextualized human behavior, which we have formalized as a human motion prediction task. Specifically, given 1 second long motion history, the task is to predict the future 3D path and pose sequence of the person. Depends on her intention, the women may take totally different future paths. We want to have multiple future predictions to model this multimodality. Our prediction should also be coherent with the scene context. For example, our model should predict this human making a turn to reach the other side, rather than directly going through a table. This task is very relevant to many real-world applications, such as smart glass for guiding vision-impaired people or home robots which provide service to the nearby passengers. They both need to understand and predict people's future movement before planning the next action. Most previous work on future 3D human motion prediction use only 3D pose history as input. Since these methods completely ignore the image context, the predicted human motion may not be physically feasible in the environment, such as walking through the wall. Some previous work used the cropped human patch to guide the future motion prediction, but do not pay attention to the background image or the global scene context. Given this limitation, the predictions tend to be short-term and local in space, that is, walking in the same spot without global movement. To understand 3D human motion constrained by the environment, we need a large-scale human scene interaction dataset with clean 3D labels. Unfortunately, we find very few datasets suitable for this task. Existing human scene interaction datasets tend to be small-scale and have relatively noisy 3D human pose annotations due to the difficulty of performing motion capture in the wild. To overcome the mentioned issues, we introduce GTA Indoor Motion Dataset in this work. We collect a large-scale dataset of diverse human scene interactions from the GTA 5 game engine. Example interactions are watching TV, laying down on a sofa, drinking, using mobile phone, sleeping on bed, etc. We collect high-resolution RGBD video with clean 3D labels such as human pose. Our data is very accurate and realistic. Here we show the 3D point cloud obtained from few RGBD images. We can script the renderer for motion sequences by assigning action episodes. When collecting the data, we are able to randomize the environment, characters and their walking style, etc. Here, we demonstrate some samples from our dataset. It has diverse indoor scenes, human characters, activities, camera viewpoints, and lighting conditions. In total, we collect 1 million RGBD images with clean labels. With this large-scale dataset, we further design a learning framework for the task of long-term human motion prediction. Here is the overall pipeline of our method. We factorize this task into 3 sequential stages. Our model first predicts the motion goals, then plans the 3D paths towards each goal, and finally generates the 3D poses following the paths. Our system takes only 2D inputs, which is an RGB image, and the 2D human pose history. Depending on his intention, the person can choose to turn left to climb upstairs, he may also go straight through the hallway or turn right to fetch some items off the table. To model this multimodality, our method first predicts multiple hypotheses of human movement goals, represented as 2D destinations in the image space. For this purpose, we employ a conditional variational autoencoder as our goalnet. The input to the model are an image and the 2D heatmaps which encode the human pose history. The model encodes the input into a latent space, from which we can sample a random z vector for decoding the destination of human movement. By sampling different z vectors, the model can have stochastic destination prediction. Given these destination predictions, our model further plans 3D path towards each destination. We design a network that exploits the destination prediction, the image, and the pose history to plan the future 3D path. A key design choice is that, instead of directly regressing 3D global coordinate values of human paths, we represent the 3D path as a combination of 2D path heatmaps and the depth values of the human center over time. We find this representation can achieve better results due to its strong correlation to the image context. We finally generates 3D human pose sequences following each predicted path. We choose to use the transformer network to model temporal human dynamics. We first back project the 2D pose history into 3D using the human center depth predicted by PathNet. The network takes this initial 3D pose as input to predict the future human poses. Now we show qualitative results of our method. We start with 3D path prediction results. In each video, we visualize the history of human center positions as green dots and predicted 3D path rendered on image plane as blue points. Here we show the per-frame prediction results on Prox dataset. For this visualization, we generate one identical prediction without sampling different goals. We also show results on GTA indoor motion dataset. Our model can predict smooth and plausible human path into the future. We next show results on 3D pose predictions. We first show the input to our method, which are an image and the 2D human pose history. On the right-hand side, we visualize the ground truth future 3D poses rendered in the 3D mesh. The motion sequence is looped for few times. On the left-hand side, we show the prediction from a baseline which does not exploit scene context. As a result, the predicted motion collides with the table. In contrast, our model can generate more physically plausible results. To avoid the collision, our model predicts the human taking a slide before standing up. Now we show another example. By sampling different goals, our method can produce multiple predictions. In this example, our model can predict the human leaning back or standing up. This is another example. Our model predicts the human is going straight in the first result while turning right in the second result. We next show the quantitative evaluation of our method. In this table, we compare to previous work on 3D path and 3D pose prediction results. We calculate the average 3D distance between the 2-second long prediction and the ground truth. Our model can outperform previous methods by a margin, 45 mm smaller in 3D path error and 20 mm smaller in 3D pose error. In this figure, we evaluate the two modes of our model. The stochastic mode that can generate multiple future predictions by sampling different 2D destinations from the goalnet, and the other mode that can generate one identical prediction without deploying goalnet. As we can see, with more samples, the 3D pose error of the stochastic model continues to decrease. This validates the advantage of doing sampling to deal with the multimodality in the future motion prediction. There are still many aspects in this problem that can be explored in the future. For example, integrating multi-view images as input can help recover the 3D scene better. The resulting 3D scene could be further used to refine the 3D pose prediction by enforcing the scene geometry constraints. Another interesting aspect to explore is to incorporate information of dynamic objects and multiple moving people inside the scene. Finally, we think it is still an open question about how to effectively evaluate the naturalness and feasibility of the stochastic human motion predictions. For more details, please visit our project page. We have released our dataset. If you are interested, please email us for access. Thank you.